Section 3.2, least squares regressions. So we've got some objectives here. We want to explain what is meant by a regression line. Given a regression equation, we want to interpret the slope and y-intercept in context. We want to explain what is meant by extrapolation. These first three objectives are found on pages 199 to 205. These ideas will be supporting those three objectives. First off, we have our definition of a regression line. A regression line is a line that describes how a response variable, y, changes as an explanatory variable, x, changes. We often use the regression line to predict the value of y for a given value of x. Now, one thing that we have learned over the years, especially in mathematics, as we work, you've seen the y equals mx plus b. Well, this is our slope-intercept equation. Our regression line is going to be something very similar to this idea, where y is our response, x is our explanatory. Now, we've also heard these called dependent and range. X you've heard called independent and domain. So that's kind of what we're going to be working on with this first section. So as we look here, we have non-exercise activity and fat gain. So the idea is that we're saying the less you exercise, the more weight you gain. So that we're saying that this is our explanatory and our response, our independent, our dependent, our domain, our range. The x, the y. So when we deal with regression lines as mathematical models, suppose that y is a response variable, vertical axis, x is an explanatory variable, horizontal axis, a regression line relating y to x. Now, this is a major difference here. Look at this option, y equals a plus bx. We're used to using y equals mx plus b. I do not know the reason for it, but the statistics world uses this. We have to use this. Do not use our old slope-intercept version of it. Now, the thing is some of the letters still mean that are the same, or I should say same definitions. This is our slope. We use b instead of m, and that's our y-intercept. So it's still the same concept. It's just a different order on how they are written. Non-exercise activity. So the idea of fat gain is that we would have a least squares regression line. So this line here would have some type of equation, y equals a plus bx, based off of this data. What this least squares regression line allows us to do is to predict. So like in this particular case, we're saying that if you can burn 400 calories a day without doing any exercise, we would predict you to gain 2 kilograms in fat. Now, this particular actual example was about 3.8 kilograms, but we would predict just over 2 kilograms. As we work with least squares regression lines, we need to be careful of something called extrapolation. Sometimes we can use these equations to predict data that's out of our range, and we'll get some data that is incorrect. Like, for example, my son Roman, he is currently at 3 feet tall, and he's 2 years old. So hypothetically, when he's 4, he'd be 6 feet tall. And then when he's 8, he'd be 12 feet tall. Well, this is an example of extrapolation. That just because Some of our data works in one range doesn't mean it's going to continue on forever and ever. Like twins, Alex and Bella. They were born at 6 pounds, about, and Alex now weighs 20. So they were 0 years old and at 6 months. And Bella weighs about 18. So she's put on 12 pounds in half a year. So feasibly, she'd weigh 30 pounds. And then after 1 year, so then 24 pounds a year, then she'd be at 54, then 78, then 102, and then 126, 150. So she'd be 150 pounds at 1, 2, 3, 4, 5, 7 years old. And well, that's not how weight gain works.